Okay, we have been discussing about the trajectory transfer. So, we continue with that. So, last time we have started working with the efficiency of the Human transfer and bioelectric transfer. So, bioelectric transfer we still did not start. So, about the Human transfer we worked out the equation that delta V, the amount of impulse required, that is given by delta V by V I, in fact that was given by 1 minus 1 by n times 2 n divided by 1 plus n. Okay, so, this was the equation that we derived last time. Now, in this equation delta V is the total impulse required and V I is the velocity in the initial orbit, and where n we defined as R f by R I, where R f is the radius of the initial circular orbit, and R f is the final circular orbit radius and R I is the initial circular orbit radius. Okay. Now, this equation gives you the amount of impulse required. So, when this impulse is going to be maximum, that we can deduct from this equation, and that will give us idea that the Human transfer we are using, how useful this is. So, if we suppose delta V by V I, if we write this as a quantity A and then differentiate this quantity with respect to n and set it to 0. So, this will give you the stationary values. Okay, so, this gives equation then gives you the stationary values. So, we start doing this. So, we will have d A by d n. So, by differentiating this, okay, equation is very complex. So, let us work it out patiently and then look into the result. So, first we have the term which is written like this. So, we will break it to simplify the whole thing. So, by breaking we can write 2 n by 1 plus n under root minus okay. So, the second term we are taking inside the square root sign. Okay. So, we have to differentiate with respect to n this quantity. So, from here what we get? So, we differentiate this first, taking this as the first term and 1 by 1 plus n as the second term, and this is under the square root sign. So, accordingly you get this quantity here. Next we take this term and differentiate this. So, the whole term here, this we can take as a single quantity and differentiate. So, this will give us under root 2 by 2. And next taking this term, So, this we are setting equal to 0. So, this quantity becomes equal to 0. So, this implies this we are using as n. So, 2 we can cancel from both sides, and this under square root 2 we can take on the right hand side. So, what we get then, and moreover few more simplification we can do. This 1 plus n square root, this term we can take from, because it is a present here in both the terms here and also here in this place. So, we can take it on the right hand side, and the square root 2, this also we take on the right hand side. So, we get here, and what else we can do, n also we can take under root n also we can take on the right hand side. So, this will give us 1 minus under root n 3 by 2 times under root root 2 gets cancelled out, and it will appear here in denominator. So, here we cancel out whatever the possibilities are there. And this term can be further simplified. So, this will yield us n plus 1 minus n. So, this is 1 by 1 plus n. This can be further simplified. This equation we can further simplify it, and this will yield us n plus 1 plus 2 n divided by this term, this will cancel out, and we get here 1 plus 3 n. Okay. So, further simplification of this, now this will give you certain polynomial, this can be reduced to a polynomial. So, after reducing that, then we need to solve it. So, here if we square on both the sides. So, what we get 2 times 1 plus 3 n square is equal to 1 plus n whole cube. Okay. And if you simplify it, so this is going to give you a equation which will appear as n cube minus 15 n square minus 9 n minus 1 equal to 0. Now, in MATLAB you can solve this equation. So, the solution to this n will appear as 0.4338, another root will be minus 0.1480, another root will appear as 15.58176. So, now in this solution, these two solutions are discarded because it contains the negative sign. N is equal to, we have written as R f by R I. Okay. So, this cannot be negative. So, these two we discard and we accept only this final solution here. So, 15.58176. So, now what we have got that n equal to 15.58176. Now, if you take the second derivative of this, the quantity A. So, by taking it and inserting the value of n in there, so this will turn out to be less than 0. So, this implies that n corresponding to 15.58176 gives the maximum value of A. So, A equal to, we have written as delta V by V I, and so this becomes maximum when n is equal to 15.58176. Okay. So, you can see that how the efficiency changes. So, if you are taking n equal to R f by R I equal to 15.58176, means this implies R f equal to 15.58176 times R I. So, if your final radius is 15.58176 times R I, then the efficiency of your Hohmann transfer is worse. Okay. Means you need at that time delta V, which will be delta V by V I, which will be maximum. Okay, in that case, means delta V is larger, then you have to spend more and more energy. The larger the value of delta V, the more and more mass of the propellant will be required. Okay, now, before we discuss further anything about the Hohmann transfer, let us go into the bioelectric transfer and look how the results appear for that. So, we do the same exercise, we try to find out delta V by V I in the bioelectric transfer also, and then we will compare both of them, how do they compare, and when the bioelectric transfer will be efficient and when the Hohmann transfer will be efficient, then we will be able to deduce. So, right now the scenario is that for n equal to 15.58, the Hohmann transfer is going to be the worst. So, in the bielliptic transfer we have started with one initial orbit of radius r I, and we had a final orbit of radius r f. So, we were giving one impulse here in this point. So, this was our starting point A, and in an elliptical orbit it was transferred here, then another impulse is required here in this place and it is taken to this point which is C. So, this is point B here. So, here we require delta V A, in this point we require delta V B, and here we require a negative impulse delta V C. Okay, so, this will point in this direction. Now, with this arrangement find out how much this delta V by V I will be. So, V I is nothing but the velocity in this initial circular orbit whose radius is r I, and similarly V f we can write for the radius in this final orbit, velocity in this final orbit. Okay, so, considering at point A, velocity in the initial circular orbit this will be given by V I equal to mu by r I under root. And V in the transfer orbit. So, we can term this trajectory as number 1 and this we can term as number 2. So, this is one transfer orbit and this is another transfer orbit. So, V t 1 velocity in the transfer orbit, similarly we can write mu times 2 by r I minus 1 by A t 1. So, from here then we can have this delta V I for trajectory 1, okay, and we need not put here 1 subscript because delta V I itself connotes the meaning that we are right now transferring here along this line. So, how much this delta V A will be. So, this you can write as delta V I or as delta V A, whichever notation you choose. So, let us put this as delta V A. So, delta V A then will be equal to V t 1 minus V I and mu by r I we can take as common. So, this leaves us with 2 minus r I by 81 under root minus 1, and mu by r I is nothing but your V I. So, this quantity times 2 minus r I by 81 under root minus 1. Now, A t is the quantity which you can look from the figure. So, A t is the semi major axis of this transfer orbit 1, and this will be equal to r I, this quantity, plus r b. R b is from here to here. So, this quantity is your R b is the Parisi apogee position of transfer orbit 1. Okay. So, from here we can say R b plus R I divided by 2, this is equal to R T 1. So, thus this is R T 1, this will write as not as R T 1, rather as A T 1. This is the semi major axis. This quantity plus this quantity, this added together divided by 2, this gives you the semi major axis of this transfer orbit. Now, inserting this A T 1 in this equation here. So, your delta V by V I then becomes equal to 2 minus R I is equal to R B plus R I is given. So, this is R I is already this is given quantity, this we have to insert. So, this is R B plus R I divided by 2. So, 2 goes in the numerator and this is minus 1. So, this becomes 2 R B plus 2 R I this will get reduced to 2 R I cancel out, 2 R B plus okay. Now, after calculating this, we need certain more workout. So, let us write now we have two quantities. Say if in this figure the ratio of the R B divided by R I, we have one quantity this R B by R I, another quantity is when we go into the final thing, which is R f is the radius of this. So, R f by R I, these are the two quantities involved in our case. Okay, so, based on these two quantities we can write certain expression. So, let us in this expression put R b by R I is equal to n star and R f by R I is n. Okay, so, depending on how do we term these quantities. So, accordingly the equation will appear. If we term this as n, so here we also instead of n star we can put here n star, but it will be more logical because n we are using as the quantity which is the ratio of the final orbit to the initial orbit radius. So, it is better that R f by R I we term as n, and the quantity which is appearing as the R b here, okay, this R b by R I we term it as n star. So, if we choose that notation, then delta V by this delta V by V I, this will become 2 R B by R I divided by, and this is minus 1 is missing here. So, we put minus 1. Okay. Now, after doing this, the next quantity that we can compute is delta V by delta V B. This is our delta V A. So, delta V B by V I. So, first we have to compute delta V B, and thereafter we will be able to find this. Now, delta V is the quantity, delta V B is the quantity that we are producing here. Here you have the velocity, once you give the impulse here, the satellite will come here in this place, and after next you give impulse here in this place. So, it will go in this place, and the third impulse is required here. So, this is called bi-elliptic, because we are putting in two different elliptical trajectory. So, one is here and another one is here, and that is why this is called bi-elliptic transfer. Okay. So, now we have V B in the trajectory T 1. So, this will be given by mu times 2 by R B minus 1 by, this is the initial one, initial velocity at this point. Okay. So, here we, in this ellipse, the semi major axis is known to us. So, that we are using here, and R B is the radius here in this point, that is known to us. So, this is the radius from here to here. So, that we have put in this place, and we use this equation for the velocity to compute this. Similarly, once we give the impulse, so we are putting it in a different trajectory. So, V B at in the trajectory T 2. So, at this point in this trajectory, how much impulse is required? So, that will be given by me by 2 by. Now, for this particular trajectory, R B does not change. So, R B remains same, but here the semi major axis will change. So, semi major axis will be summation of this and this divided by 2. So, we can write A T 2, this is equal to R B plus R F divided by 2. So, this is 1 by A T 2 under root, where A T 2 is R B plus R F divided by 2, and A T 1 is R I plus R B divided by 2. So, now from this we will have delta V B now inserting the value for A T 2 and A T 1. So, this will get reduced to let us take again the mu by r I time outside. Okay. So, if we take mu by r I under root outside. So, this will become 2 r I by r b and 82 is nothing but r I plus r b plus r f divided by 2. So, 2 will come upside. Similarly, we take from here mu by r I outside. To r I by r b minus 2 r I by r b plus r I under root. So, then delta V b, now mu by r I under root, this quantity is nothing but V I. So, we can take it outside and write here in this place. Now, r b by r I we have written as r star. So, this becomes 2 by n star, we have written 2 by n star under root minus, okay, this quantity again we here divide the up and down numerator and denominator by r I. So, this becomes r b by r I is nothing but n star and r f by r I is nothing but n. Similarly, this quantity has to be inserted here. So, this is 2 by r b by r I is n star minus 2 divided by r b by r I will be here n star and plus 1. So, this is the quantity we are getting here. So, now let us term different equations. This is the equation number 1. Okay, here we can do little bit more simplification, in that we can take n star 2 by n star outside. So, 2 by n star we are taking it outside. So, this becomes 1 minus 2 goes outside. So, this will become 1 by, okay, and here further simplification is possible here in this place. So, we can do the first simplification and rather later on we will take it outside. So, we will have 2 times n star plus n divided by similarly here in this place. Okay, now we will take outside 2 by n star under root. And this is our equation number 2. Now, after working this, we go into the next level. So, now we have to find delta V at C. So, we proceed in the same way. So, delta V C we can write as 2 mu by R f. This is the velocity at delta V C equal to velocity at C minus V C in the transfer orbit 2, okay, or either V f minus V C 2 or V T 2 also you can write. So, V f, let us write separately. V f now becomes equal to 2 mu by R f minus 1 by A T 2 under root. Mu is outside, and similarly the V, this is the velocity in the transfer orbit. So, we write here V C T 2 and V f we write as mu by R f under root. So, this is at position C, the velocity in the transfer orbit, which is the elliptic orbit. So, for this we have got this equation, and in the circular orbit this is the final velocity. So, delta V C, now this will be equal to delta V C by, okay, delta V C first we write, this will be V C T 2 minus, okay, here the quantity that we have written, we can write either as V f minus C T 2 or V C T 2 minus V f. Okay. Here this will turn out to be negative, because finally, in that circular orbit your velocity will be smaller than that in the elliptical orbit. So, rather writing in this way, we could have put here the sign minus here and the plus here in this place. So, it will get into this shape. So, now in this equation this quantity will turn out to be positive. So, delta V C that we indicated with a negative sign in our figure. So, here this delta V C quantity will be negative, and with minus sign this will turn out to be positive. So, that is, you have to apply the impulse in this direction and reduce the velocity. So, this will get into this orbit. So, from here then this results in 2 by R f minus 1 by A T 2 times mu under root minus mu by R f under root. So, take mu by R f outside. So, delta V C becomes mu by R f under root, we are taking outside. So, this becomes 2 minus R f by A T 2 under root minus 1. And now, the quantity which is present here, this is nothing but your the velocity in the final circular orbit. So, here this becomes 2 minus 2 R f by to R f by R f plus R b. E t 2 is R f plus R b by 2. So, this will appear in this way. Here we can divide numerator denominator by R I. And this will become 2 R b divided by R f plus R b. And this quantity is nothing but mu R I is V I, and R f by R I is nothing but n. Okay. And here similarly we can divide numerator denominator by R I. So, this will become 2 by R b divided by R I and R f by R I plus R b by R I under root minus 1. So, this is V I by under root n, and 2 R b by R I is nothing but R b by R I is we have taken as n star. Similarly, R f by R I we have taken as n. So, this is n star. Now, you have got the velocity change in the 3 positions. So, this is our equation number 3. One more step we will write here. So, we have delta V by B c by V I equal to 1 by under root n times 2 n star divided by n plus n star under root minus 1. So, from here total delta V will be equal to delta V A plus delta V B plus delta V C, and this we divide by V I. So, this will be the quantity. Now, from all the 3 equations we add. So, this is our equation number 3. So, adding equations 1, 2 and 3. So, the very first equation we had 2 n star divided by n star plus 1 under root minus 1, and then the second equation we got this is 2 by n star under root times under root and plus the third equation which is present here. So, 1 by n under root to n star by n plus. So, this n star we can divide here in this place. This quantity can be written as 2 divided by 1 plus n divided by n star under root. So, we write in that way. So, this will be 2 divided by 1 plus n star under root and minus 1. Okay, now we have got this final equation, and from here you can get a lot of insight into the equation. So, now the only way for working out this, you can choose the different values of n star. Okay, this can be solved also, and ultimately it will look like in the form of a polynomial, and from there then we will start working out. But the best thing is here in this case that this delta v by v I that we have written, we can choose certain value of n star and then start giving different values to n and then plot the result. So, by plotting you get the graph for delta v by v I. So, if you plot that, so here n star will appear as a parameter. So, this is basically a parametric, it will appear in the form of a parametric study. So, now go back into our old thing. Okay, one of the study what we can do, here we have got this equation, this will, let us name this as equation number 4, to write a phrase here in this place. This is 2 n star divided by this is our equation number 4. Now, question arises whether the Hohmann transfer and bielliptic transfer, they will coincide at certain place. So, for that you need to solve this equation 4. So, when the Hohmann transfer and bielliptic transfer will coincide. So, for this purpose we need to solve equation 4 and for the Hohmann that we wrote this is the equation that we wrote for Hohmann. So, let us term this equation as this equation, let us say this may be, we write in Roman notation this as 1. Okay, so, solve equation 4 and 1 which is referring to Hohmann transfer on first page. So, by solving this we will be able to tell in what place they will coincide, but before we do any further exercise, let us look into the plot of the Hohmann and bielliptic transfer. Now, we have already calculated that the maximum of the Hohmann transfer, it occurs at for n equal to 15.58176. So, if we make a plot of this, plotting n on this x and delta v on this x, which is in kilometer per second, and this we do for a orbit of, for a circular orbit, of radius equal to radius of earth. So, this is called the grazing orbit. Okay. So, this is being worked out for this grazing orbit. Now, if we do this for grazing orbit and take the final orbit to be 3 here, final orbit R f by R I ratio to be equal to 3. So, we start with this value. Okay, so, corresponding to this value here we will have a value of 3.11. Okay, and this curve will, this is the Hohmann transfer curve, and this will go like this, and then for Hohmann transfer, and the maximum of this occurs at 15.58176. And that maximum value is here 4.23. This is 4.23. So, delta V equal to 4.23. So, in the Hohmann transfer you can see that the maximum change in velocity occurs for n equal to 15.58176. On the other hand, if we take the bielliptic transfer, which is given by the equation that we have developed earlier here, okay, and in the next lecture we are going to explore it. So, the bielliptic transfer, it will appear and this is for n star equal to infinity. So, n star equal to infinity means in the intermediate radius in the bielliptic transfer is taken to be infinity. So, for that case we will see that the Hohmann transfer and the bielliptic transfer, they intersect at a point 11.93876, which is nearly equal to 11.94. Okay. So, they match at only at this point. So, in the next lecture, once we explore this, we will see that between 0 to 11, your Hohmann transfer is the best, and thereafter between from 15.58176, this bielliptic transfer this will turn out to be the best. Okay. So, overall what the picture we are getting here, that Hohmann transfer, the change in velocity required to do the changes for R f by R a equal to 3 is 3.11, and till 15.58 Hohmann transfer it remains till 11.94, till this range Hohmann transfer remains the best, and thereafter in this range bielliptic transfer or Hohmann transfer which will be good, because this is for the n star equal to infinity. So, we have to further explore it, and we will discuss further on this in the next lecture. Thereafter, the Hohmann transfer it becomes not so energy efficient, but this curve is more energy efficient, because lesser change in velocity is for achieving the same value of n, you would need the lesser velocity change, and that implies that you need lesser amount of fuel. So, here the maximum velocity change is required at this point for the Hohmann transfer. So, this corresponds to 15.58176. So, as you increase the radius RF by RI to 15.58176, this is the maximum amount of velocity change will be required. Okay. That is, you have to spend more amount of fuel here in this case. And between this range, it is a little dubious, but before here the Hohmann transfer is the best, because it requires less amount of delta V, that you have to give less impulse, and therefore, less amount of fuel consumption, okay. And therefore, the Hohmann transfer it remains the best in this range. Okay. So, we can write here that the Hohmann transfer is best if n is less than 11.94, okay. And rest other we have to explore further, that what will happen beyond this range. Okay. So, Hohmann is best for this case, and we will continue with this lecture further, deriving how to get this point 11.94, where these two, the bioelectric and the Hohmann transfer curve intersect, and discuss more about the properties of this. So, we continue in the next lecture. The time is getting over. Thank you very much.